Okay, we shall begin by talking about sample proportions. Okay, proportions are essentially a percentage. We use proportions when we're thinking about how many out of the total. Essentially, when our sample or our thing or our experiment or whatever is a yes, no. That makes sense. This many were for it, this many were against it. A lot of our other ones, we were doing like SAT math and everybody had a score, so you average their scores. That's a mean. Okay. And proportions work sort of like means. They do just if they get large enough, they distribute normally. Okay. The mean of a sample proportion is the number of people in my sample times the proportion. So the example they had above had 510 people, and the proportion was 205 out of 510, I think. Guess what that works out to be? Oh, the 205 that responded in ways, let's say yes. The standard deviation, unlike your normal complicated formula for standard deviation, is actually a relatively simple formula. NP times 1 minus P. So in my case of what's there, 510 times 205 over 510 times 1 minus P would be 305 over 510. It's basically NP is the number 4, and 1 minus P is the proportion against. Okay. Or N times proportion, 4 times proportion against. And we're going to see that a lot. Oh, that's for random variables. Sorry, this is my standard deviation formula for proportions. It's square root of P times 1 minus P over N. Okay. Sorry, correct that. This is the standard deviation formula. Now, in order for this formula to be valid, there's a there's some rules of thumb, they're called, or things that you need to check. Um, in order for that to work, your population must be at least 10 times the size of your sample. This is rule of thumb number one. And what we're going to end up doing a lot after break is checking conditions. And we're going to be doing some stats tests that allow us to estimate how accurate my actual sample mean is. So gives me estimates on my actual population. But those estimates only work if the conditions that the test can be used in are actually true. Otherwise, you're like making some assumptions and doesn't matter. You can't make conclusions on bad data, poorly collected data. If the data is collected really poorly, you cannot draw accurate conclusions from it. Oh, I want to estimate the mean height. Well, I went out and haphazardly just looked for tall guys and picked 10 of them. And yeah, mean height for guys at this school is 6'2". That's not true, but you cannot use that. So one of these is that your population has to be at least 10 times the size of the sample. And if it's not, you probably might as well just have used a census, in which case you don't need. Then if you properly censused and you actually included everybody, you got your results. You don't need to do anything else. That makes sense? The second rule of thumb, this one's not great down the scan, but this says that my distribution will be approximately normal. So if NP is greater than or equal to 10 and N1 minus P is greater than or equal to 10. Well, NP is the cases for, and N1 minus P is cases against. So I must have at least 10 people on each side of that. That makes sense. And if I do, I can say my distribution of proportions will be approximately normal, which is going to allow us to do all kinds of things with it. So example, applying to college. A polling organization asks an SRS of 1,500 first-year college students whether or not they applied for admission to other colleges other than the one they're attending. In fact, you finished math, didn't you? Yeah. You just need to go tell them that you don't have to take English. I'm gonna pause, wait for Noah to get back. Apparently, they need a better system for knowing who and doesn't have to actually test. I'm not sure what that good better system is, but apparently they need a better one.
Can you define sample distribution?
Remember last week we had that distribution of like we do 1,000 samples. That's a sampling distribution. You know that what you have is one within all the possible samples. So the sampling distribution is all the possible samples that could exist. Oh, by the way, you did hit your growth goal in map. So did Noah.
There were a few questions where I knew the problem. And then after I clicked next, I realized, oh, I did that wrong.
And you can't go back on that test, can you? Well, apparently you still grew enough. This class did great. 3 for 3. And 0 for 0 over on that side of the room. Did you enjoy your 0 for 0 on map test? But this side of the room did 3 for 3.
Oh, yeah. I took like 20 minutes of that. Wait, yeah, right?
Yes.
Yeah.
Oh, I did see a pile of items. Right?
Did you send a picture?
No, but
Yeah.
I have everything. Was that?
My second hour class talked me into giving them a point of extra credit. I was like, I can extend it to first hour for those that did.
Didn't know about that.
No.
I had big jugs. It was really big. That was cut into pie slices.
That's the one up in like Ashton, isn't it?
I mean, I know. It's pretty big for a very pretty pie.
Pretty pie shaped.
Like 16, 13 invoice. We bought like 4 pounders.
I sure.
That doesn't seem like enough for 16.
When I was.
You'd need at least 8. Or did you buy 2-pounders? Feel like you need at least a half pound each for
Yeah,
teenage
2
boys.
big. We didn't eat all 3 burgers, so we just kind of sitting. I guess I didn't actually know how
Hmm.
it seemed like a lot though.
Okay, back to recording. So, how can we use this? First we need to test a few things. Is the population more than 10 times the size of the sample? We had 1,500 first-year college students, and 35% of them applied for another college other than the one they're going to. Is the population of first-year college students more than 10 times my sample size of 1,500? Yes. First year, there's way more than 15,000 first-year college students. And then I must check condition number 2. And it is important that you write this out. N is 1,500. P is 0.35. Somebody with a calculator in front of them can do that. No, I'm going to have you do the other one. Holman does this one. So 1 minus 0.35 is 0.65, correct?
Yeah.
Okay. Okay, that's bigger than 10. I mean, I could know these without actually multiplying them, then. That should be 975, I believe.
Yeah.
Those are both bigger than 10. Okay, we could use our formulas. So our standard deviation formula, square root of p, 0.35, 1 minus p, 0.65 over 1500 equals 0.0123. And I can approximate this to normal. So this is a normally distributed. It asks me what's the probability of being within 2 percentage points. So I can use my normal distribution. 2 percentage points less is 0.33, right? And that gives me a z. Oh, come on. Doesn't tell me. Okay, what does that equal? Negative 1.62, 63. So look up negative 1.63 z tables in the front.
Zero, 5, 1, 6.
And this is going to be symmetric because it said within 1.2. So I'm not going to calculate 0.37. It's going to be give me the same thing outside. What's the percentage in the middle then? 1, which is the whole thing, minus 2 of those, which is 0.8968. Nearly 90% of the time, this poll will give us results within 2 percentage points. Not quite, but nearly. Probably close enough for round off. Maybe I should make it 1550 or something, and then I'd actually get there. But go, okay, that's pretty good, right? So survey under coverage, and they use this kind of a lot. One way of checking the effect of undercoverage, non-response, and other sources of error in a sample survey is to compare the sample with known facts about the population. When this book was made, about 11% of American adults are Black. The proportion p hat, remember p hat is my sample proportion, p being my population, and population goes with parameter, sample goes with statistic, was only about 9.2. We suspect that something about our sampler procedure is somehow underrepresenting Blacks. We will find the probability that that a sample contains no more than 9.2% Blacks if the population is 11%. So first off, is the population more than 1,500 adults, 15,000 adults? Are we at least 10 times the size of my sample? Yeah. NP and 1 minus P. NP is, any way you do it, they're both greater than 10. There's listed down here, 165. 1,500 times, we do the actual assumed P here of 0.11, not the collected P hat. Is 165 and 1335. Both are much larger than 10. So we're going to do our normal. They calculated the mean here to be 0.0, or the standard deviation to be 0.00808. So I do my normal distribution. And when we calculate that, what do we get?
Negative.
And when we look that up, we get
It was like that. That was, it was wrong. Yeah, you're going up. 0 to 1.
just over 1% chance. I think something about this survey, somehow, some way, intentional or not, underrepresented the Black population. Whether it was just non-response or whatever, but there is an underrepresentation here.
Yeah.
Okay. So that's 9.2. We're now on to 9.3, sample means. So that's how we do it with proportions. This is how we do it with means. We're skipping over this one. First thing we're going to talk about is the standard error, sort of. The standard error actually involves S, but the standard deviation of my means is the standard deviation of the individuals divided by square root of my sample size. Okay, so this is standard deviation Izzy, you're taking a test. Keep it down. That makes sense. So the larger the sample size, we noticed that the distribution got narrower on Thursday in the last lesson on 9.1. So young women's heights. The height of young women varies approximately according to the distribution N64 2.5. 64.5, 2.5. And what does that mean again? What does N stand for? No, capital N in this distribution thing. We only know two types of distributions so far. B is binomial. What's N? Normal. Normal. What's the 64.5? Or 5, 4.5. How does that relate to young women's heights?
Oh, was it the?
That's the mean. What's the 2.5? Standard deviation. So, suppose we choose an SRS of 10 young women. The sampling distribution of the means, well, the mean of the sampling distribution is always the same mean. But the standard deviation, so mu of x doesn't change. The standard deviation, though, I now have to divide my standard deviation of the individuals by the square root of the sample size, giving me the standard deviation of my means of 10 young women is going to be 0.79 inches, which ultimately means it's going to, as I take these averages, narrow it.
That's the
Standard deviation of means, yes. If my sample size went to 100, it'd be 2.5 over square root of 100, which is 0.25. Standard deviation just keeps getting smaller. But it does not get smaller linearly. So, using that, if I have a young woman at 66.5, what is the probability of mean height of 10 young women is greater than 66.5? So if I do it for a single young woman, I get 0.8 and I get a probability of 21.19%. Very possible, right? Reasonable chance, 1 in 5. However, if I take an SRS of size 10 and I average them, now I have to do this new standard deviation of 0.79, which gives me a probability of 0.0057, less than 1% chance that my sample of 10 will average a height over 66.5 or 56.5. Okay. And they show down here these distributions. Look at how much they're both normal, but look at how much it narrowed when we had 10 observations. 100 is going to narrow it a lot more. Which does kind of make some logical sense, doesn't it? So, the central limit theorem, you need to know this by name. So I would get this in your notes. And what this practically means is if I have an SRS, simple random sample of any population with mean, mu, standard deviation, sigma, if n is large, we're later going to define large as more than 40. Moderately large being more than 20. But if n is large, my sample means will be approximately normal, period. Doesn't matter how non-normal my data is. So if my distribution looks like this, if I have a sample size of that's sufficiently large, more than 40, maybe more than 50, depending on, but we're later going to define it with slight variation on more than 40. My means will distribute normally. Yes, there is a very small chance I could pick everything from over here. But it's a very, very small chance. That makes sense? And yes, I basically made some random scribble for a distribution where I tried to make it as weird as possible. The central limit theorem, and this has been proven, says that the means, if there's a sufficiently large sample size from that population, the means will distribute normally. So looking at it in action, and here we've got some distributions. This is my distribution for individuals. Which way is it skewed? This is right. Yes, the tail's on the right. It's based on the tail. Look at what happens to this very skewed distribution when n is 2. It's definitely not normal, but it's getting closer. At n is 10, we got this little skewed tail off here. But otherwise it's pretty normal. By n is 25, that looks awfully normal. Doesn't it? The sample mean of 25. And I believe they do that with a bunch of calculus that you guys don't know yet, but okay. Servicing air conditioners. So if you take a service call, a lot of them are short, right? You know, usually if something's not working, it's usually a simple fix. But it could be a very long fix. There's no actual maximum time this could take, right? So the time for a technician requires to perform preventative maintenance on an air conditioning unit is governed by the exponential distribution whose density curve appears in figure 19.7a. Okay, that's this one back here. With mean time 1 hour and standard deviation also 1 hour. Okay. So this is not normal, but mu equals 1 hour, sigma also equals 1. And your company operates 70 of the units. What is the probability that the average maintenance time exceeds 50 minutes? Okay. So, first off, rules of thumb. Well, there are way more than 70, correct? This isn't a true SRS, but there's way more than 10 times 70 in the population of air conditioning units. Um, and well, I guess I don't have to do rules of thumb. This isn't proportions. 70 is more that is sufficiently large that I can say that this will approximate to normal, correct? And I can calculate the standard deviation 1 over square root of 70, which is 0.120 hours. I can calculate a z-score for 50 minutes. 50 minutes is 5/6 of an hour, right? That's a 0.120. What's 5/6 minus 1 is negative 1/6. What's negative 1/6 over 0.120? We're looking for, this is the 50 mark. This is the 60 mark. We're looking for this side. So I need to do 1 minus what I get in the table, right? So tell me, what is the probability that the average time exceeds 50 minutes? .922. So, yes, there is pretty good chance it's going to be over 50 minutes. I bet you the median is less than 50 minutes, though. Any questions on this?